The strangest stars in the universe take us on a journey through some of the most extraordinary stellar phenomena, from the baffling dimming of Tabby's star to the explosive flares of V838 Monocerotis, and from the massive R136A1 to the enigmatic white dwarf Sirius B. These celestial wonders push the limits of our understanding of stellar evolution and the very physics that shape the universe. Join us as we unravel their mysteries and explore the profound astrophysical insights they offer.
Stars with unusual light phenomena and dimming events. Some of these strange objects are stars that have short-lived random dimming events that make us question how stars usually behave. These strange events make us think about the rules that control how bright stars are. They also bring up interesting ideas about how material around stars affects their brightness, how stars change on their own, and maybe even the signs of advanced technology from other planets. This part goes into more detail about the strange things that happen when light changes quickly. It looks at one of the most well-known cases and what these short-lived events mean for our understanding of how stars work. Tabby's star, KIC 8462852, whose mysterious dimming events have puzzled scientists since it was discovered, is one of the most talked-about cases of strange light phenomena. The star was first found in the Kepler dataset as KIC 8462852, and it quickly gained attention when scientists noticed that its light dropped by up to 20% in strange, seemingly random ways. Tabby's star's brightness drops randomly and deeply, which doesn't fit with any known orbital mechanics. This is different from the regular dimming seen in eclipsing binary systems or passing exoplanets. Several ideas have been put forward to explain these strange fading events. One popular natural theory is that the star could be surrounded by a cloud of comets or other objects that are orbiting it. In this case, the uneven dips could be caused by a cloud of cometary pieces or dust that periodically blocks the star's light. This model is appealing because it is simple, but it has trouble explaining the size and depth of the dimming, as well as the lack of a major infrared excess that would usually be present with a lot of dust around the star. Some ideas that are based on speculation have also been put forward. Some experts have even thought that the dimming might be caused by alien megastructures, which are huge man-made structures built by a more advanced society to use the star's energy. People are very interested in this theory, but it is still very controversial and is only used as a last option when all natural explanations have been tried and failed. Newer studies, on the other hand, point to intrinsic unpredictability as a possible reason. This means that Tabby's star might have a strange internal structure or dynamic processes that make its brightness change randomly. Even though a lot of observations have been made with ground-based cameras and space projects, no one knows for sure what is causing Tabby's star to dim. Its light curve is hard to put into a single category, and no single model has been able to fully explain all the things that have been seen. What's so interesting about this star is that its strange behavior forces scientists to go beyond their current ideas and think of new ways things might work in very harsh stellar environments. Standard models of stars usually assume that their brightness stays mostly the same over short periods of time, with only small changes happening during well-known events like eclipses, pulsations, or changes in spin caused by star spots. But the random lowering events don't follow these predictions. They make us think again about how complicated the processes are that control how bright stars are. The issue that these short-lived events cause is that we have to figure out how to explain events that don't happen at regular times within the context of star development. Based on the idea of steady nuclear fusion in the core of a star, traditional models have a hard time explaining rapid, deep drops in light that don't happen at regular times. Since there is no pattern, it's likely that the dimming isn't caused by a simple geometric arrangement like a partner object or a passing exoplanet. Instead, it could be caused by more random or chaotic processes. Because of this, scientists are looking into how the star and its surroundings change over time. They are thinking about things like changing material around the star, sudden explosions of mass, and interactions with a complicated magnetic field. Brief light events make us think again about how energy is made and spread inside stars. If the star's light changes quickly without the usual signs of pulsation or spin, it could mean that other processes are at work. These could include changes in the dynamics of convection, instability in nuclear fusion, or even unknown ways of moving energy around. These new ideas make us question how simple current models are, and urge us to create more complex simulations that can show all the different ways stars can behave in the worst situations. Studying temporary events can help us learn more about how stars die and come back to life. Dimming events that can't be explained may be signs or precursors of big changes in evolution, like the start of a supernova or a star changing into a different class. Astronomers are looking at the time, depth, and length of these events in order to find early warning signs that a star is entering a very important stage in its growth. This knowledge is very important for both theory models and figuring out what will happen in our own cosmic neighborhood in the future. The problems that brief light events cause also affect how we observe them. In order to better record these brief events, traditional studies and tracking programs might need to be changed. This has led to the creation of new methods in time-domain astronomy. As our tools get better and our data gets bigger, we'll probably find more stars that behave in strange ways. Each new finding will put our theories to the test even more and help us learn more about how stars are different and change over time. Stars with chemical peculiarities and magnetic extremes. A star that was first listed as HD 101065 and is now commonly known as Przybylski's star is one of the most interesting cases in this group. Astronomers are very interested in this object because it has a very strange chemical makeup. Its spectrum is mostly made up of too many rare Earth elements and other heavy metals, while elements that are usually found in the atmospheres of stars look surprisingly low in number. The usual models of nucleosynthesis say that elements made inside stars should be spread out more evenly. This feature makes those models questionable. The strange chemistry changes in the star suggest that it must be going through some special physical processes. One theory is that the atmosphere makes diffusion processes work better, which means that heavier elements fall and lighter ones float. This creates a stratified, non-standard makeup. Another possibility is that the strange pattern of abundance could be related to the past of stars merging or the addition of chemically different matter to the area around it. No matter what caused it, the fact that there is such a strange case pushes scientists to rethink how stars make and spread elements. Models that were thought to be reliable for a long time are now under a lot of pressure to include these rare cases, which could mean learning new physics or changing how we think about magnetic diffusion and radiative levitation. As scientists keep working to improve spectroscopic methods and make more complex models of stars, this chemically unusual star serves as a stark reminder of how complicated things are behind the uniform glow of stars. A star called Babcock's star, which was first named HD 215441, is also very interesting because it is very magnetic. This object has one of the highest magnetic fields ever recorded in a star, with strengths that are much higher than what is usually seen. This star's strong magnetism changes how we think about how stars form and evolve, especially when it comes to how magnetic fields affect how energy moves and how things happen on the surface. The strong magnetic field in these kinds of stars can stop convection, change how energy moves from the inside to the outside, and even change how mass is lost and how rotational momentum changes over time. These kinds of fields can put more magnetic pressure on a star's atmosphere than heat pressure, which can make the surface very organized and sometimes spotty. These magnetic spots and regions can make strange spectrum fingerprints that, when studied, can tell us something about how the star works on the inside. Such a strong field also makes us wonder where it came from. Is it a fossil field, something left over from when stars were younger, or is it being actively made by a dynamo process in the star's convective layers? Looking into these magnetic extremes isn't just a way to learn about the quirks of a single star. It has bigger effects on all stars that are chemically unusual. It is known that strong magnetic fields can stop the mixing of chemical elements in the atmospheres of stars. This may help explain why some stars have strange patterns of abundance. Also, Babcock's star's strong magnetism can be used as a natural testbed to see how theories of magnetohydrodynamics work in harsh conditions. This could lead to new ideas that can be used to explain a lot of different astrophysical phenomena, from how plasma behaves in the space between stars to how accretion disks move around compact objects. A star with strange chemical properties and a star with strange magnetic properties are both examples of how differences in how stars behave can lead to new theories and questions about old ones. They tell us that the universe is not a flat area with clear rules. It is a changing place where extremes are the standard rather than the exception. As more observations are made and technology improves, our measures and models get better. These stars continue to show us the different ways that stars evolve. They are very important places to test ideas that try to explain how stars form, change over time, and add new elements and magnetic phenomena to the universe. Stars with dramatic outbursts and sudden changes. Big explosions and sudden changes go against the idea that stars are steady, predictable light sources. Instead, they show a secret side of stellar development that is marked by instability and quick change. These amazing events can show up as intense flares, sudden brightening, or even sudden decreases in brightness. Each one gives a brief look into the complex processes going on inside a star or in its immediate surroundings. Such outbursts could be signs of important changes in a star's life, leading up to big events like supernovae, or they could be caused by mass ejections and interactions with matter in the area. V838 Monocerotis made a big splash in astronomy in 2002 with an outburst that didn't follow the usual pattern for stars. Unlike most novae and supernovae, this one had a sudden and huge rise in brightness followed by a very sudden drop in brightness. Astronomers are still not sure what caused this. During the event, the star got several orders of magnitude brighter in just a few weeks, but it quickly went dim again. But what really caught people's and scientists' attention was the amazing light echo that appeared. This is when light from the outburst bounced off of cosmic junk and formed rings of light that grew around the star. This result not only made the sky look beautiful, but it also gave scientists a unique chance to learn more about the star's surroundings and how far away it is. A lot of people have strong opinions about how V838 Monocerotis erupts. One of the most popular ideas is that the explosion was caused by a stellar merger, which is a big crash between two stars. In this case, the brightness increase might be due to the energy released during the union, while the fast decrease in brightness could be due to the cooling and growth of the stellar envelope that followed. So the light echo is like an afterimage in space. It shows us the complicated structure of the dust around us and gives us clues about how the merger happened. Some other ideas say that the event could have been caused by a late helium shell flash, which is a thermonuclear runaway on the surface of an old star that causes a short, powerful phase of higher light. But the strange spectral and photometric qualities seen during the outburst are more in line with the merger theory. This is especially true when you consider the eruption's uneven light curve and multiple peaks. Detailed spectroscopic studies of V838 Monocerotis revealed unusual chemical signatures and temperature changes that supported the idea of a rapid, chaotic reconfiguration of the star's outer layers. The light echo further allowed astronomers to map the three-dimensional structure of the circumstellar environment as different layers of dust responded to the flash of light at different times. This phenomenon has proven invaluable for distance measurements and for understanding the distribution of material around the star. Even though there isn't a single theory that everyone agrees on yet, the star merger idea is currently the best way to explain V838 Monocerotis' strange behavior. The rapid release of energy and the complex light echo are both explained by this, High-resolution images from cameras like Hubble are still being used to study this. In the early stages of their lives, some stars suddenly and dramatically become brighter. This can last for decades and completely changes how they look, showing how rapid mass accretion works. A young star called a V838 star that is known for its dramatic explosion is a well-studied example of this behavior. This event, which is marked by a quick rise in brightness, often by several magnitudes, is thought to be caused by a sudden, runaway accretion event from the ring of stars around the young star. The V838 event questions our usual ideas about how stars change over time. Instead of getting brighter slowly as a protostar develops, these events show that stars can go through big growth spurts every so often. The most popular theory says that when there are problems in the protoplanetary disk, which could be caused by changes in gravity or temperature, material suddenly floods onto the surface of the star. This fast accretion not only makes the star much brighter, but it also heats up its outer layers, which changes its spectral properties in a way that makes these outbursts different from the normal changes that happen in stars that are older. Observations of these outburst events have revealed a wealth of information about the physical conditions in the circumstellar environment. For instance, during the eruption, the star's spectrum shows broadened absorption lines and a shift toward cooler, redder temperatures over time, indicating that the expanding, heated disk material plays a significant role in the overall emission. This process effectively resets the star's evolutionary clock, enabling it to accrete large amounts of mass in a relatively short period. Such episodes can dramatically influence the future evolution of the star, potentially dictating its final mass and setting the stage for subsequent stages of stellar development, including eventual stabilization as a main sequence star. The V838 event has bigger effects on the development of planetary systems than just the effects on the star itself. The fast, rough accretion events can do a lot of damage to the ring around the star, which could affect how planets form and move. In some cases, the energy released during the surge may cause volatile chemicals to evaporate or dust and gas to be moved around, which could change the structure of any new planetary system that forms. So, these one-time events aren't just interesting facts about stellar physics. They're essential to understanding how young stars and their planetary systems change together. The study of these amazing events is also important for testing theory models of disk instability and accretion physics. The goal of astrophysicists is to find the exact processes that cause these outbursts by comparing detailed observations with complex computer simulations. Are gravitational instability problems inside the disk the main cause, or do magnetic fields and heat processes play a bigger role? Even though we still don't have all the answers, our knowledge of these complicated processes is getting better as we keep observing and modeling them. These studies not only put light on the early stages of a star's rapid growth, but they also make us question our larger ideas about how stars form, giving us new ways to think about the balance between order and chaos in the universe's early days. Stars with erratic brightness and instability. There is a small group of stars that stand out because their brightness and steadiness are so hard to predict. It is not normal for stars to change brightness in a straight line over time, but these stars' brightness changes dramatically over days, months, or even years. This kind of irregular behavior is often a sign of underlying physical processes that are complicated and not well understood. These can be anything from pulsational instabilities and turbulent mass loss events to complex interactions with material around them. According to experts, watching these strange things in the sky will help them figure out what causes such big changes and learn more about the harsh conditions inside stars. Betelgeuse is one of the most well-known red supergiants in the sky. Astronomers have been interested in it for a long time because of its strange changes in light and the possibility that it will explode as a supernova in the future. As a massive star that is getting close to the end of its life, this heavenly giant shows changes in brightness that are both biologically interesting and give us a hint of the turbulent processes going on inside its huge convective envelope. Over the past few decades, observations have shown that Betelgeuse's brightness doesn't stay the same. It changes a lot over time. There are several reasons for these differences. There are large convection cells on the surface of the star, which is a major factor. In contrast to the Sun, where granulation patterns are mostly small, Betelgeuse has huge, turbulent areas that can cover a large part of its surface. These convective cells can rise and fall, causing the star's photosphere to heat and cool unevenly. This can cause changes in light that can be seen. The star's upper layers also go through pulsations, which are regular expansions and contractions that change how much light it gives off. These pulsations are caused by complicated interactions between the star's internal pressure and gravity. They can cause cycles of getting brighter and darker that don't follow simple patterns. Yet another factor that makes Betelgeuse change is the way dust moves around in its world around the star. As a red supergiant, Betelgeuse is losing a lot of mass, sending stuff into space that can cool down and form dust. Changes in the amount and spread of this dust can block the star's light, causing it to suddenly become less bright. In the past few years, a dramatic and surprising dimming event has caused a lot of attention and discussion in the field of astronomy. Some people thought the star might be about to explode in a supernova, but more research showed that the dimming was probably caused by more dust around the star, not a direct sign that the core was about to collapse. Betelgeuse's general features strongly suggest that it is getting close to the end of its stellar evolution. As a red supergiant, it has used up most of the nuclear fuel in its core and is going through fast changes that will end in a supernova explosion. People think that the changes in brightness are signs of this advanced stage of evolution, a time when there is a lot of chaos, mass loss, and complicated internal dynamics. When Betelgeuse finally goes supernova, it will be a spectacular event that could be seen during the day and give scientists new ways to study the universe. Not only would this kind of explosion change the way we see the star itself in a big way, but it would also teach us a lot about how massive stars die and how our galaxy's chemicals get mixed together. Eta Carinae is one of the most mysterious and studied luminous blue variables, LBVs, in our galaxy. It is known for its dramatic events of losing a lot of mass and being naturally unstable. As a massive star in the late stages of its growth, it has had dramatic explosions that change both its structure and the interstellar medium around it. The star, Eta Carinae's great eruption in the middle of the 19th century, is one of the most important events in its history. During this time, it became one of the biggest things in the sky for a short time and threw out a huge amount of matter. The beautiful homunculus nebula was made from the material that was thrown out. It is a bipolar structure that shows the dramatic past of this stellar giant. The extreme mass loss exhibited by Eta Carinae is a key characteristic of LBVs. Massive stars like Eta Carinae are inherently unstable due to the delicate balance between the outward pressure from radiation generated by nuclear fusion in their cores and the inward pull of gravity. In Eta Carinae's case, this balance is disrupted by an enormous luminosity that drives powerful stellar winds, ejecting vast quantities of mass into space. These winds can reach speeds of several thousand kilometers per second, stripping away the outer layers of the star and profoundly affecting its evolution. The loss of mass not only influences the star's brightness and temperature, but also alters its internal structure, potentially precipitating further instability and subsequent eruptions. Astrophysicists face a huge task when they try to model such bright blue factors. The moving parts that control LBVs are complicated and include things like turbulent flow, radiative pressure, and fast-spinning effects. Extreme conditions near Eta Carinae push the edges of current computer models. This is because high-resolution multiple simulations are needed to show how radiation and hydrodynamic forces interact in a star that is losing mass at such a fast rate. Also, the fact that the mass loss events happen in spurts and are followed by times of silence makes it harder to predict how it will change over time. Not only does Eta Carinae lose mass, but its light and spectral properties change a lot over short periods of time, which is another sign of its instability. It is thought that changes in the star's outer shell cause changes in temperature and brightness. These changes are caused by interactions between pulsations and radiation forces. It's hard to make uniform models of LBVs when their behavior is so complicated because the physical processes at play can be very different from one event to the next. Eta Carinae is also close to other massive stars in a dense cluster, which adds more factors like binary interactions and outside effects that can make the system even less stable. Although these interactions may help start or change explosions, they make it even harder to figure out what the star's basic features are. Massive and luminous stars. Some of the heaviest and brightest things known, these colossal stellar giants are the very end of star formation and are powerful engines that drive the growth of galaxies. Their huge masses fuel very high levels of nuclear fusion in their cores, which makes them so bright that they can light up whole galaxies. Their strong radiation and stellar winds have a huge impact on the areas around them. When we look at these huge stars, we find things that don't fit neatly into any one category. These include red supergiants that get so big they're scary luminous blue variables whose strange changes in brightness suggest that they are unstable, and hypergiants that go beyond what is physically possible. The way that these stars' high mass, energy output, and dynamic processes interact with each other questions our models of how stars evolve and gives us important new information about how mass is lost, how supernovas start, and how the universe gets more chemicals. Some stars are truly titans, huge, powerful beings whose sheer size and brightness push the limits of what we think is possible in the universe. These star giants, which include some of the biggest and brightest objects known, amaze scientists with how much energy they put out and how quickly and violently they change their behavior. Their huge masses cause nuclear fusion to happen at speeds that make them bright enough to light up whole galaxies. The strong stellar winds and dramatic pulsations seen in these stars give us important information about the outer limits of how stable stars can get. By studying these huge stars in more depth, we learn not only about the physical processes that control their life cycles, such as how they lose mass quickly, how they experience high radiation pressure, and how they might explode in a supernova, but also about how they have a huge effect on the evolution of the galaxy and the enrichment of chemicals. Our 136A1 is one of the most amazing stars we know of. It is a record-breaking star whose mass and brightness make us question what the limits of star formation are. This heavyweight giant has changed what scientists thought was possible in terms of stellar mass and energy output. It is located in the dense and colorful R136 cluster in the Tarantula Nebula, which is a famous starburst region in the Large Magellanic Cloud. It's hard to believe how heavy this enormous light is. It is thought to have a mass more than 250 times that of the Sun, which would make it one of the heaviest stars ever seen. Because it has such a huge mass, nuclear fusion can happen at an unheard-of rate, which makes it shine brighter than 10 million times the Sun. Not only does such a bright output light up the area around it, but it also has big effects on how the host starburst region works. This star sends out a lot of energy and strong stellar winds that change the shape and structure of the space between the stars. This causes new stars to form and affects how nearby molecular clouds change over time. In starburst regions like the Tarantula Nebula, conditions are extraordinarily conducive to the rapid and efficient formation of massive stars. The presence of such an extreme object provides critical clues about the processes that drive star formation under these intense conditions. The extraordinary mass of the star, coupled with its exceptional luminosity, challenges traditional models of stellar evolution, which often struggle to explain how such massive stars can form and remain stable for even a fraction of the cosmic time predicted by theory. In particular, the immense pressures and turbulent environments within starburst regions demand that any viable model of star formation account for rapid accretion, significant mass loss, and the delicate balance between gravitational collapse and radiative feedback. This titanic beacon serves as an empirical benchmark, testing the limits of these models and offering a unique opportunity to refine our theoretical frameworks. The study of this heavy giant has also led to progress in both observed astronomy and theoretical astrophysics. Modern cameras have made high-resolution imaging and spectroscopy possible, which have given scientists a lot of information about the star's atmosphere. They have found strange spectral fingerprints and huge differences in temperature. Scientists use these findings to figure out how the star's internal mechanics and energy transport systems keep it shining so brightly without breaking apart from the radiation pressure. Also, the information we get from this object is very important for figuring out what happens to the biggest stars in the end, whether they explode in a spectacular supernova or fall straight into black holes. V838 Monocerotis is one of the most amazing red hypergiants, which are a very rare type of star that shows the very end of stellar growth. This huge object is one of the biggest stars known. Its width is several thousand times that of the Sun, which goes against what we think we know about how stars form and change over time. Its huge size not only makes it a beautiful sight to see, but it also lets scientists study the processes that control how the biggest stars die and come back to life. Red hypergiants are characterized by their vast, extended atmospheres and significant instability. The sheer scale of these stars leads to intense gravitational forces in their interiors, which in turn drive enormous amounts of energy outward. In the case of this stellar titan, the tremendous energy output creates powerful stellar winds that strip away the outer layers over relatively short periods, compared to more stable stars. These vigorous mass loss episodes are critical in shaping the evolution of such stars, as they determine both the remaining mass available for nuclear fusion and the eventual fate of the star. The interplay between mass loss and radiation pressure in red hypergiants is a key factor that limits their longevity and sets the stage for their explosive end, possibly as a supernova or even a direct collapse into a black hole. The way a red hypergiant is put together is just as interesting. Because it is so big, its upper shell is very long and spread out, and it often has problems with convective instability. There is a lot more convection in these stars than in stars like our Sun that are smaller and closer together. This causes big, rough movement inside the envelope, which adds to the uneven changes in warmth and brightness. What scientists have seen is that these stars' light output changes all the time. This may be because the outer layers of these stars are constantly changing and becoming unstable. These pulsations and convective movements not only show us how red hypergiants are structured on the inside, but they also change how mass is lost, since turbulent flows create shock waves that push matter away from the star. The extraordinary size of these hypergiants challenges existing theoretical models of stellar evolution. Standard models, which work well for less massive stars, struggle to account for the extreme conditions within these giants. For instance, the high luminosity and low surface gravity create conditions where radiation pressure plays an outsized role, often leading to the formation of a complex, clumpy circumstellar environment. This environment is rich in dust and gas, which can obscure the star and complicate measurements of its properties. Additionally, the enormous mass loss observed in these stars indicates that their evolutionary pathways may diverge significantly from the predictions of classical theories, suggesting that alternative processes, such as episodic eruptions or enhanced convective mixing, might be at work. Astronomers learn a lot about how the most huge stars die and come back to life by studying something so far away. Researchers can improve models of how stars evolve and learn more about how red hypergiants add to the chemical enrichment of the space between stars by looking at their spectral features, changes in brightness, and rates of mass loss. The material that these stars throw out into space, which is full of heavy elements made in their cores, provides the building blocks needed to make new stars and planets. luminous blue variables, and hypergiants. The bright blue variable star, P Cygni, is one of the most well-known in our galaxy. It has been studied for hundreds of years, and its unique spectral profile, which is made up of strong emission lines and blue-shifted absorption components and is called the P Cygni profile, shows that it has very strong stellar winds. The star is dropping mass at an amazing rate, as shown by these winds. The sudden changes in brightness seen in P Cygni are typical of LBVs. They have dramatic outbursts that cause light to rise quickly, followed by times of relative quiet. This kind of change is caused by the careful balance between the star's strong gravitational pull and the powerful radiation pressure that pushes matter outward. This interaction leads to periods of mass loss, which can change the shape of the star's envelope and impact its future growth. S. doratus, which is often thought of as the model for bright blue factors, acts in a similar way. Its brightness changes a lot over time, and these changes can last for years or even decades. Like P Cygni, S. doratus has dramatic outbursts when its brightness goes up, and its temperature may drop for a short time. This is thought to be because its outer layers expand and contract during times of heavy mass loss. The random changes seen in these stars go against common models of stellar development, which usually assume that energy output and mass distribution stay pretty steady. LBVs like P Cygni and S. doratus, on the other hand, show that the life cycles of the heaviest stars are marked by periods of unrest and dynamic change. P Cygni and S. doratus show how light blue variables change over time, but Eta Carinae is an interesting example of a hypergiant star, which is a type of star known for its huge size, extreme brightness, and equally dramatic changes over time. Eta Carinae is known for having big changes in its spectrum and unpredictable changes in its brightness. These features set it apart from stars with less mass and show how complicated the processes are inside these huge stars. Both the amount of light that Eta Carinae gives off and its spectral features change a lot. The star's spectrum shows big changes in temperature and ionization levels over time, which means that the star's outer layer is changing quickly. These changes in the spectrum are closely linked to times when a lot of mass is lost and the structure becomes unstable. Like other LBVs, Eta Carinae goes through outburst stages where the star grows and cools, temporarily shifting its color toward red. During quieter times, however, it shrinks and gets hotter, which flips these spectral traits. This repeating pattern shows that hypergiants are naturally unstable and also shows how delicate the balance is between the pull of gravity and the huge radiation pressure inside the core. When compared to other hypergiants, Eta Carinae's variability is particularly striking due to its amplitude and rapidity. Its light curve reveals fluctuations that can occur over relatively short timescales, suggesting that the processes driving these changes are both highly dynamic and possibly multi-layered. The interplay of pulsations, convective activity, and episodic mass ejections creates a complex picture where the star's overall structure is in constant flux. In this context, Eta Carinae serves as a natural laboratory for studying the mechanisms of stellar instability. Researchers are keen to understand how such massive stars can endure periods of extreme variability without undergoing immediate catastrophic collapse, and what these cycles reveal about the later stages of stellar evolution. Therefore, studying Eta Carinae not only adds to what we know about how stars behave individually, but it also has larger effects on models of how stars evolve. By looking at its changes in brightness and unpredictability compared to those of other hypergiants, astrophysicists can find similarities and differences that help them understand the physics behind these stars. Comparing things helps us learn more about how mass is lost, how convection works, and the final paths that lead to supernova explosions or straight fall into black holes. Stars with irregular and semi-periodic luminosity. Astronomers have found HR 5171a, a yellow hypergiant that goes against our usual ideas about how stars evolve, to be one of the biggest stars they have ever seen. This huge star is amazing not only because of its size, but also because of how it behaves. Its width is thought to be more than 1,300 times that of the Sun. Its huge size and brightness go beyond what normal theories can explain, which makes it an important testbed for learning about how massive stars die and come back to life. The sheer scale of HR 5171A brings into focus several challenges in modeling stellar evolution. For one, stars of such immense size are expected to be inherently unstable. Their extended outer layers are subject to intense convective motions and pulsational instabilities, which can lead to episodic mass loss. In the case of HR 5171A, these instabilities manifest in irregular brightness variations and significant changes in its spectral characteristics over time. Traditional models of stellar evolution, which work well for stars like our Sun, or even for moderately massive giants, often struggle to incorporate the chaotic processes at play in hypergiants. The interplay between the outward pressure of radiation and the inward pull of gravity becomes particularly delicate in such extreme conditions. As HR 5171A expels mass through powerful stellar winds, it loses part of the fuel required for nuclear fusion, thereby altering its evolutionary trajectory in ways that are not fully understood. In addition, HR 5171A's huge brightness, which is caused by its huge mass, adds to the problems. The huge amount of energy released causes strong radiation pressure, which can make the star's upper layers even less stable and cause more mass loss. This self-regulatory process, in which losing mass changes the structure and development of the star, sets off feedback loops that make theoretical models harder. Astrophysicists have to use very complex multiple models to figure out how these huge stars move and change over time. These models try to show the finer points of convective flows, pulsations, and radiative transfer, but there are still a lot of unknowns, even with today's powerful computers. The fact that it's hard to model such extreme stars shows that we don't fully understand how stars work, which suggests that there may be other unknown factors affecting the stability and growth of hypergiants. Studies that focused on observing HR 5171A have given us a lot of useful information that helps us make these models. Astronomers have been able to study the star's outer layers using high-resolution spectroscopy and interferometry. This has shown them complicated velocity fields and uneven patterns of mass ejection. These findings show that the star's atmosphere is not smooth. Instead, it is made up of a mix of rough areas that all contribute to the star's light and spectral output changing over time. Deneb, also called Alpha Cygni, is a bright supergiant star that fascinates scientists with its brightness changes that happen every so often and give us information about how unstable huge stars can be. Deneb's brightness changes irregularly and only slightly on a regular basis, which is different from stars that pulse in expected cycles. This suggests that Deneb has complex internal dynamics and an unstable outer envelope. This strange behavior gives us a unique look into the physics of supergiants and makes us think about how energy moves around and is lost in such huge stars. Keeping an eye on Deneb for a long time shows that its brightness doesn't change in a strict cyclical pattern, but instead changes in a way that is kind of random. These changes are probably caused by large-scale pulsations in the star's thick atmosphere. The balance between radiation pressure and gravity forces is very unstable in supergiants like Deneb. Small changes can cause big changes in the structure of the star. The changes in light that happen every so often might be caused by the interaction of radial and non-radial pulsations, which are waves that move through the star's layers. The star regularly grows and shrinks because of these pulsations, which in turn change its warmth and brightness. But the fact that these movements don't happen in a straight line suggests that other things are at play, like turbulent convection and localized mass ejections, which makes the picture of a simple rhythmic pulse more complicated. The variability in Deneb's light curve has profound implications for understanding the instability of supergiant stars. It indicates that the processes governing these stars are highly dynamic and susceptible to small changes that can have large-scale consequences. The irregular nature of the brightness variations challenges conventional models of stellar pulsation that rely on well-defined periodic cycles. Instead, Deneb exemplifies how supergiants can exhibit chaotic behavior due to the inherent instability of their vast, tenuous envelopes. This instability not only affects the star's luminosity, but may also play a role in its long-term evolution, potentially influencing the rate of mass loss and the eventual fate of the star. Spectroscopic studies of Deneb give us more information about how it works on the inside. Over time, changes in the spectral lines show that the velocity fields inside the star's atmosphere are shifting. This suggests that different parts of the star are moving in and out of sync with each other. This complicated behavior might be caused by how pulsational modes, convective processes, and the star's spin all work together. By looking at these changes in spectral lines, scientists can figure out more about the structure and motion of Deneb's upper layers. This gives them useful information that helps them make better models of supergiant stars. Deneb's semi-periodic variability also affects how we think about the development of stars in the higher levels of the Hertzsprung-Russell grid. Deneb is one of the brightest and heaviest stars, so it plays a key role in the life processes of stars. Its ability to change could be a sign of deeper processes happening before more dramatic evolutionary events like supernova blasts. Researchers are looking at Deneb and comparing it to other variable supergiants in order to figure out the physical processes that control the last stages of massive star development. This will help them understand how these stars go from safe burning phases to explosive ends. Stars with unique evolutionary histories. HD 140283, commonly known as the Methuselah star, is one of the oldest known stars in our galaxy, serving as a remarkable fossil from the early universe. Its ancient age, along with its distinct chemical makeup, provides critical insights into the conditions of the primordial cosmos and the processes that govern the formation of the first stars. In this exploration, we delve into the star's age determination, its unique chemical signatures, and the profound implications these properties have for our understanding of the early universe. A lot of scientists have thought a lot about and argued about how old the Methuselah star is. With an estimated age of almost 14 billion years, it is getting close to the age of the universe, which is about 13.8 billion years. To find out such a young age, you need to take exact measures of the star's qualities, like its brightness, temperature, and metallicity, and use models of how stars evolve. The star has a very low metallicity, which means it doesn't have many elements heavier than helium. This means it formed when the universe was still chemically simple. Heavy elements had not yet been made in big amounts in the early universe. Because of this, stars that formed during that time are likely to have low metal contents. The very low amounts of metals in the Methuselah star support the idea that it came from almost pure matter that existed right after the Big Bang. Spectroscopic analyses reveal that its atmosphere is almost entirely composed of hydrogen and helium, with only trace amounts of heavier elements. This scarcity of metals is not only consistent with a formation in the early universe, but also challenges our understanding of the processes of chemical enrichment over cosmic time. In more chemically evolved stars, elements like carbon, oxygen, and iron are more abundant due to generations of stellar nucleosynthesis and supernova explosions that have seeded the interstellar medium with these products. The Methuselah star's deficient metallicity indicates that it has experienced very little contamination from later stellar generations, preserving a chemical fingerprint that is as close as we can get to the primordial universe. Studying its spectral lines allows astronomers to test models of nucleosynthesis and the evolution of the first stars, offering clues about how the earliest stellar populations influence subsequent galactic evolution. The Methuselah star is also used to test theories about the universe in the real world. Because of how old it is, we can set our own lower limit on how old the world is. If this star really is almost 14 billion years old, it means the universe is at least that old. This finding backs up readings from the cosmic microwave background and large-scale structure studies. This coming together of stellar astrophysics and cosmology makes our current knowledge of the timeline of the universe stronger. It also shows the possible problems that can happen when stellar ages get close to the expected age of the universe. This kind of situation makes us look into the unknowns in both models of star development and cosmological factors. This leads to better observational methods and theory frameworks. The Methuselah star is important for more reasons than just its age and makeup. It also gives us clues about the conditions and processes that existed in the very beginning of the world. Its presence proves that stars were formed very early, when the universe was still getting back to normal after the Big Bang. This very old star shows that the primordial gas clouds, which were mostly made up of hydrogen and helium, were able to collapse under their own gravity and form stars, even though they didn't have any heavy elements that help cool star-forming areas that are newer. This changes some standard ideas about how quickly stars form and makes scientists rethink the role of molecular hydrogen and other ways to cool things down in a place with few metals. Astronomers also learn about the life processes of the first-generation stars, which are sometimes called population 2 or even population 3 stars, by studying how the Methuselah star changed over time. Even though population 3 stars haven't been seen directly yet, the Methuselah star helps us learn about their qualities and how the universe changed from being empty to being filled with stars through successive generations of stellar nucleosynthesis. Its chemical trace, which has been kept, is like a time capsule because it shows us what the temperature, density, and radiation fields were like when the universe was first forming. These results have very important effects. Not only do they support what we already think about how the universe evolved over time, but they also show us where our knowledge is lacking. To show that the age of such a very old star fits with other cosmic data, for example, stellar evolution models need to be carefully calibrated. This could even lead to new ideas about how the universe began. The Methuselah star is also one of the oldest stars in the Milky Way, which makes it a very important tool for measuring how well and when chemical enrichment processes happened in the past. Stellar end-of-life and cataclysmic events. Sanduleak, minus 69 degrees 202, is an important star in the history of astronomy because it is the parent star of Supernova 1987A, which is the closest supernova ever seen. It was thought that only red supergiants could be the precursors to such catastrophic events, but this star, a blue supergiant in the Large Magellanic Cloud, proved them wrong. It finally exploded in 1987, giving scientists a chance to study in detail what happens during a supernova explosion, from the core of the star collapsing to the rich material being spread out into the space between the stars. Prior to its explosion, Sanduleak minus 69 degrees 202 was an unusual object in its own right. As a blue supergiant, it was characterized by high temperatures, intense radiation, and relatively low levels of hydrogen in its outer layers, a stark contrast to the cooler, more extended red supergiants that were traditionally associated with supernova progenitors. The star's evolutionary path posed a significant challenge to existing stellar evolution models, which struggled to explain how a star could evolve from the main sequence to a blue supergiant phase and still retain sufficient mass to explode as a supernova. The case of Sanduleak minus 69 degrees 202 prompted astrophysicists to reconsider the roles of mass loss, rotational mixing, and binary interactions in shaping the evolution of massive stars. The explosion of supernova 1987A provided a one-of-a-kind testbed for these updated models. Observations made at bands ranging from radio to X-rays helped scientists figure out how the explosion happened and how a complicated remnant was formed afterward. In this case, finding neutrinos from the explosion proved that the core collapse was followed by a burst of these almost massless particles, just as theories had expected. Also, the supernova remnant's later changes, including its growing rings and uneven ejecta, helped scientists figure out how the parent star's outer layers were put together. These findings not only supported some parts of the core collapse supernova theory, but they also showed that we need more complex models that take into account the different ways that huge stars evolve. The study of Sanduleak -69°202 and its supernova has helped us learn more about how galaxies get more chemically rich. Heavy elements in the world come from supernovae, and the unique nucleosynthetic fingerprints seen in supernova 1987A have helped scientists figure out where these elements came from in later generations of stars. The unusual traits of the parent helped explain how the elements were distributed in the area, making a direct link between the last stages of evolution of a star and the chemical evolution of the galaxy that hosts it. V1309 Scorpii is a beautiful example of a bright red nova, which is a short-lived astronomical event that is now often seen as proof that stars join into one. Luminous red novae are thought to happen when two stars in a close binary system circle together and join, releasing a huge amount of energy. This is different from supernova explosions, which are very powerful. Observers can tell when this kind of event is happening because the brightness suddenly rises, but then slowly fades over months or years. There is also a unique red color that means the material being thrown out is cooling. In the case of V1309 Scorpii, extensive photometric and spectroscopic monitoring revealed a progressive brightening, followed by a sudden peak and a subsequent decline in luminosity. Detailed analysis of the light curve and spectral evolution provided compelling evidence that the event was not a typical nova or supernova, but rather the result of a stellar merger. Prior to the eruption, the binary system exhibited signs of orbital decay, gradual tightening of the orbit, as the two stars lost angular momentum through tidal interactions and mass transfer. When the stars finally coalesced, the merger released a burst of energy that dramatically increased the system's brightness, while the ejected envelope cooled to produce the observed red spectrum. As V1309 Scorpii shows, the brilliant red nova phenomena provides a special insight into the mechanisms of star contact and coalescence. It emphasizes how, when gravitational forces and angular momentum loss cooperate to push stars in binary systems together, they can experience extreme alterations. Though smaller than in a supernova, the energy emitted in such a merger is nevertheless adequate to eclipse the combined light of both progenitor stars for a period. Crucially, the result of the merger leaves one single, more massive star behind, which may pursue an evolutionary path different from that of either of the original stars. The development of binary systems and our knowledge of star demography depend much on this process. By stressing the function of near-binary contacts, the study of brilliant red novae like V1309 Scorpii questions establish theories of solitary star development. The fact that many stars exist in binary or multiple systems implies that mergers may be more frequent than formerly believed, maybe helping to produce exceptionally big stars or bizarre objects that do not fit cleanly into conventional evolutionary models. Such mergers also offer a natural explanation for some of the unusual chemical abundances and structural abnormalities seen in some stars, as the mixing of material from two different stellar cores generates distinct signals not created by single-star evolution. Furthermore, the study of V1309 Scorpii has advanced time-domain astronomy as scientists create more advanced monitoring systems to identify these transient phenomena. Our knowledge of the dynamics of star mergers has been enhanced by detailed study of the pre-merger period, the outburst, and the consequent development of the remnant. Astronomers can better control the physical mechanisms at work during these spectacular events, energy dissipation, angular momentum loss, and mass ejection by contrasting the observable data with theoretical models. White dwarfs and peculiar binary evolution. Among the most well-known white dwarfs in the heavens, Sirius B is a remarkable illustration of the terminal stage of stellar development for intermediate mass stars. Being the friend of Sirius A in the well-known binary system, it offers a special laboratory for researching the conversion of a once massive star into a compact degenerate entity. Originally, a bright, brilliant star able to maintain active nuclear fusion in its core would have been the source of Sirius B, but the star ran out of nuclear fuel over millions or maybe billions of years, and finally gravitational forces overcame the outward pressure produced by fusion. A white dwarf, a dense star remnant mostly made of electron-degenerate matter, emerged from this fall-off. The small scale of Sirius B against its great bulk is among its most amazing features. Though its mass is quite like that of our Sun, it is compressed into a volume like that of Earth. White dwarfs are distinguished by their great density. Electron degeneracy pressure is the main resistance against gravitational collapse. Investigating such things has advanced our knowledge of the basic physics of degenerate matter and the quantum mechanical interactions operating at such severe settings. Especially, the presence of white dwarfs such as Sirius B supports actual evidence for the idea of degeneracy pressure as the force stopping the collapse of dead stars, therefore verifying theoretical predictions made almost a century ago. Sirius B also exhibits several atypical properties that continue to intrigue astronomers. Its spectral characteristics, for instance, reveal a relatively cool surface temperature compared to the much hotter progenitor star. This cooling is a gradual process, as white dwarfs radiate away their residual thermal energy over billions of years. Studying the cooling curves of objects like Sirius B provides astronomers with a cosmic clock that can be used to estimate the ages of stellar populations in our galaxy. Furthermore, subtle variations in its observed spectrum have offered clues about the composition of its outer layers, contributing to our understanding of the processes of chemical diffusion and gravitational settling in white dwarf atmospheres. The evolutionary interaction between the two star partners is another feature of curiosity in the Sirius system. Being a more massive star, Sirius A affects the orbital dynamics and, in some measure, the development of its partner. For models of binary evolution, especially with regard to mass transfer and angular momentum loss, the existence of a white dwarf in a binary system such this has significant ramifications. Though now Sirius B is a solitary white dwarf, its ultimate characteristics most certainly derive from prior encounters with Sirius A. Understanding the larger population of binary systems depends on these interactions, particularly those that could finally result in events like Type Ia supernovae, strong explosions vital for cosmic distance measurement. RRA offers a convincing instance of unique binary evolution, whereby the interaction of two closely circling stars generates odd and intricate dynamical behavior. RRA presents astronomers with a rare chance to investigate the orbital mechanics and mass transfer mechanisms resulting from two stars in a gravitationally linked interacting couple as an eclipsing binary. Periodic eclipses in these systems offer exact timing information that lets scientists monitor orbital period fluctuations and deduce structural changes in the system throughout time. RRE has among its most remarkable characteristics unusual orbital dynamics. RRA has changes suggestive of major interactions between its star components, unlike most eclipsing binaries with somewhat steady orbits. One can ascribe these deviations to numerous elements. First, the stars in such a system are generally close together, which generates significant tidal pressures that could deform their forms and influence their rotational and orbital properties. This distortion not only affects the timing and depth of eclipses, but also complicates the general dynamics, thereby maybe changing the orbital period over time. Shifts in eclipse timings seen in RRA suggest that the orbit is changing, probably in response to mass transfer or angular momentum loss between the stars. A fundamental mechanism driving near-binary system evolution is mass transfer. One of the stars in our RRA is thought to be in an advanced evolutionary level and could be losing mass to its companion. The redistribution of mass disrupts the gravitational equilibrium and can either cause the orbit to shrink or expand, therefore resulting in major changes in the dynamics of the system. Not only does the orbital period, but also the spectrum properties of the stars as accreted material may change the surface composition and temperature of the acquiring star. The complexity of mass transfer in RRA emphasizes the difficulties of modeling such systems, where even small changes in the rate of mass exchange may have significant long-term implications on the binary development. The interaction of the RRA stars transcends basic mass transfer. The system's behavior is probably further complicated by a mix of gravitational forces, magnetic activity, and perhaps even pulsational fluctuations. Sometimes these interactions can produce phenomena like fluctuations in orbital eccentricity, or even the transient creation of accretion disks around one of the stars. Subtle changes in the spectral lines of RRI have been found by detailed spectroscopic investigations, suggesting that the atmospheres of the stars are always changing under the effect of both internal pulsations and dynamic consequences of their binary interaction. The unusual orbital dynamics of RRA have wider consequences for our knowledge of binary development. Many of the stars in our galaxy are part of binary or multiple systems, and interactions such as those observed in RRA can greatly affect the evolutionary paths of the participating stars. Mass transfer in near-binaries, for instance, is believed to be essential for the production of unusual objects such as blue stragglers, type Ia supernovae, even some types of neutron stars and black holes. Variable and pulsating stars. Beta Cephei variables are among the fascinating family of pulsating stars known for their fast, periodic brightness variations that provide a window into the turbulent interiors of big stars. Among this class, one outstanding object is BW Vulpeculae, a star whose strong pulsational activity has attracted much attention. Dramatic, short-period oscillations in its light curve offer insightful analysis of the physical mechanisms causing pulsations in large stars. We investigate the processes behind its fast pulsations, how these pulsations fit into the larger framework of pulsating variables, and contrast its features with those of traditional Cepheid variables in this talk. Beta Cephei stars, including BW Vulpeculae, are typically massive hot stars that exhibit variability on timescales of a few hours. The pulsations in these stars are driven primarily by the kappa mechanism, which is linked to the opacity variations in the stellar envelope. In the case of BW Vulpeculae, periodic expansions and contractions of its outer layers occur as a result of the interplay between radiation pressure and the star's internal structure. The kappa mechanism operates in zones where certain elements, notably iron, become partially ionized. In these ionization zones, an increase in temperature leads to an increase in opacity, temporarily trapping energy within the star's envelope. This buildup of energy eventually results in an outward pressure that drives the star to expand, causing the opacity to decrease and allowing the energy to escape, which in turn leads to a contraction. This cyclical process produces the rapid, rhythmic pulsations observed in its light curve. Evidently, BW Vulpeculae has become a pillar for knowledge of the pulsation dynamics in Beta Cephei variables. High-precision photometric and spectroscopic investigations show that its brightness fluctuations are not only fast, but also accompanied by matching changes in spectral line profiles, therefore implying considerable movement in its stellar atmosphere. The star's outer layers cool as it expands, and the spectral lines move correspondingly. During contraction, these lines move back to reflect changes in velocity. This pulsational activity offers restrictions on mass, radius, and internal composition, therefore providing a natural laboratory for studying the interior structure of large stars. The study of BW Vulpeculae's pulsations has broader implications for the field of astroseismology. the science of probing stellar interiors through oscillations. By analyzing the frequencies and amplitudes of these pulsations, astronomers can infer details about the star's internal density and temperature profiles, much like seismologists use earthquakes to study the Earth's interior. In the case of beta Cephei variables, the rapid pulsation periods, typically on the order of a few hours, are a direct consequence of their high temperatures and significant mass. The energy transport processes in such stars are dominated by radiation, and the delicate balance between gravitational forces and radiation pressure plays a critical role in establishing the pulsation modes. There is a different place in stellar development for standard Cepheid variables, which have pulsation times that last from a few days to months. Although their pulsations occur in colder, less massive stars, Cepheids pulsate mostly owing of the kappa mechanism. Thanks to their well-defined connection between pulsation times and inherent luminosities, these stars have proved priceless standard candles in determining cosmic distances. Although their basic physics is identical, beta Cephei and Cepheid variables differ in mass, temperature, and pulsation timeframes, which reveals different regimes of star structure and development. Representing the beta Cephei class, BW Vulpeculae fills the high-mass, high-temperature end of the spectrum and provides additional information to that which Cepheids provide. The rapid pulsations observed in BW Vulpeculae are indicative of a more volatile and less stable evolutionary phase compared to the relatively steady pulsations of Cepheids. In massive stars, these rapid oscillations can lead to significant mass loss over time, influencing their evolutionary paths and eventual fates. For instance, the pulsational instability may act as a precursor to more dramatic events, such as supernova explosions, by gradually eroding the star's outer layers and altering its internal structure. Understanding these processes is critical for constructing accurate models of stellar evolution, particularly in the context of massive stars where small changes in mass and energy can have profound long-term consequences. Studying BW Vulpeculae helps one to obtain insights beyond its immediate pulsational activity. They assist in the refinement of theoretical models that explain how pulsation modes are produced and damped, how energy is carried inside a star, and how these modes interact with the magnetic field and spin of the star. Guiding thorough studies of objects like BW Vulpeculae, advanced computer simulations are progressively showing the complex interaction of physical processes controlling star pulsations. These models provide a dynamic perspective of star development that questions stationary ideas by not only helping to explain the observed fast pulsations, but also forecast minute fluctuations in pulsation modes over time. Irregular and sudden faders. A closer look at hydrogen-deficient stars. The well-known exemplar of this fascinating class is the venerable Eta Carinae borealis variable. Renowned for its abrupt and spectacular dimming episodes, this star may drop several magnitudes in a few weeks. These sudden drops can be mostly explained by the development of carbon-rich dust in their atmosphere. The process starts in these stars when the star exparts material from its outer layers. The atmosphere supports the condensation of carbon into dust grains due to the hydrogen shortage of the star, and result of advanced nucleosynthetic processes and large mass loss. Once sufficiently dense, these dust clouds hide the light from the underlying star surface and gather in clumpy, irregular shapes. As the dust settles into the line of sight, the star's luminosity falls dramatically, sometimes to levels where it becomes almost invisible to the naked eye. Over time, the dust either disperses or is blown away by stellar winds, allowing the star to gradually regain its brightness. This cycle of dimming and recovery can occur sporadically, with intervals of relative stability interrupted by sudden declines. The study of these events is particularly challenging because the processes of dust condensation and dispersal operate on short timescales and are influenced by complex interactions between the star's pulsations, temperature fluctuations, and atmospheric dynamics. Spectroscopic analyses of this variable revealed an atmosphere that is peculiarly deficient in hydrogen, while showing anomalously high abundances of carbon and other heavy elements. This chemical makeup is critical for the dust formation process, as the scarcity of hydrogen reduces the competition for carbon atoms, allowing them to bond together more easily into dust grains. The peculiar light curves and spectral features of this class of stars have spurred numerous theoretical models, many of which seek to explain how such drastic changes in brightness can occur without significantly altering the underlying stellar structure. These models incorporate a variety of factors, from pulsational instabilities to magnetic fields, all of which might contribute to the episodic nature of the dimming events. Although no single model has yet achieved universal acceptance, the consensus remains that the interplay of hydrogen deficiency and dust formation is central to the behavior observed in these enigmatic objects. V482, a member of the same hydrogen-deficient class that shows comparable but quite different dimming behavior, is another intriguing item in this group. V482 has several of the defining traits of its more well-known relative, including abrupt brightness drop brought on by obscuring dust cloud development. Though the fundamental processes seem to be the same, the behavior of V482 provides special understanding of the variety within this stellar range. Studies show that V482 dimming events have different amplitudes and lengths of time compared to other devices in the same class. Its light curve isn't smooth, which suggests that while the process of dust creation is a common theme, the patterns of variability could be caused by differences in the star's mass loss rate, the nearby atmosphere, or even the strength of the magnetic field. Photometric tracking of V482 in great detail has shown that its drops can be both short and long, and that the time it takes to rebound varies a lot from one event to the next. These differences are very important for understanding how even small changes in physical factors can cause stars with similar chemical properties to behave in very different ways. Spectroscopic studies of V482 further highlight its unique status within this group. Although its spectrum shows the characteristic hydrogen deficiency and enhanced carbon abundances, there are subtle distinctions in the line profiles and emission features that point to variations in the dust composition or the dynamics of mass ejection. Such differences may arise from variations in the star's evolutionary state or from the influence of binary companions, which can alter the circumstellar environment through gravitational interactions. By comparing the behavior of V482 with other members of its class, researchers can refine their models of dust formation and mass loss, offering deeper insights into the complex interplay of forces that govern these transient events. In addition to helping us learn more about how hydrogen-deficient stars work physically, studying V482 also has bigger effects on how stars evolve. Close comparisons between V482 and its neighbors are a natural way to study how changes in the star's starting states, like mass, composition, and binarity, affect their evolution paths. Comparing things is important for coming up with a single idea that explains the wide range of behaviors seen in this group of variable stars. Rapid rotators and magnetic variables. One of the most interesting of these things is a star, which is known for its very fast spin and strong magnetic field. Due to centrifugal forces, this star's fast spin greatly changes its shape, making it bulge at the equator. Because it spins quickly, its magnetic dynamo action is amplified. This makes the magnetic field strong and organized in a way that isn't typical. When fast spinning and high magnetic strength come together, they create strange changes in light that happen on a regular basis, and sometimes don't. According to the data, this star's light changes in a way that makes it look like it has big magnetically active spots on its surface. As the star spins, these areas with stronger magnetic fields come and go from view, which causes changes in the brightness that can be seen. This change in light looks a lot like sunspots on our own sun, but it's much bigger and changes more quickly. But unlike solar activity, these patterns are caused by a mix of things, such as the very fast spinning speed and the strength of the magnetic field. This creates light curves that make us think about how stars change over time. The magnetic field itself is believed to play a crucial role in regulating the surface activity of the star. Strong magnetism can suppress convective motions in localized regions, creating spots that are cooler and therefore darker than the surrounding photosphere. Additionally, the rapid rotation leads to a phenomenon known as gravity darkening, where the equator, being less gravitationally bound, emits less light than the poles. The interplay between these effects produces a complex light variation pattern that has been the focus of numerous photometric and spectroscopic studies. Scientists are learning more about magnetic activity in huge stars by studying this star that spins very quickly. Astrophysicists have improved models of stellar dynamos, which show how magnetic fields are made and kept in stars because of its strange behavior. In this case, the fast spin makes the dynamo mechanism work better. This creates magnetic fields that might have an effect on mass loss, the change in rotational momentum, and even the way chemicals are arranged in the atmosphere of the star. High-resolution spectroscopy was used to map the star's magnetic field shape, which showed a structure that is not at all like a simple dipole. This detailed map helps us understand how these magnetic fields change over time and impact the whole life cycle of a star. A magnetic O-type star is another interesting example from this group. It is known for having a strong magnetic field that is well organized and a spectrum that changes a lot. The spectral lines of this star change over time, which shows that its outer layers are changing a lot and that its magnetic environment is changing all the time. Its behavior is a lot like that of other magnetic stars, but the changes in its spectrum tell us a lot about the physical processes going on inside such extreme objects. The star's magnetic field is among the strongest known for O-type stars, influencing the behavior of its stellar wind and the structure of its atmosphere. The magnetic field channels the outflowing material, often creating confined streams or magnetically dominated regions that lead to observable modulations in its emission and absorption lines. These spectral features vary as the star rotates, revealing an intricate interplay between the magnetic field and the wind dynamics. Observations have shown periodic changes in the intensity and profile of certain spectral lines, suggesting that the star's magnetosphere is highly structured and perhaps even asymmetric. Such variability is key to understanding how magnetic fields influence mass loss, angular momentum distribution, and the overall evolution of massive stars. While both this magnetic O-type star and its fast-rotating cousin have strong magnetic fields, their observed behaviors are very different in ways that are important for theoretical models. When looking at a star that spins very quickly, the main focus is on how rotation affects gravity darkening and magnetic spot modulation. But for this O-type star, the focus moves to the impacts of stellar winds that are limited by magnetic fields and the changes in spectral line profiles that happen as a result. Detailed spectroscopic tracking shows that the star's environment changes shape as it spins, which causes its spectral traits to change in cycles. Because of these findings, magnetohydrodynamic (MHD) models have gotten better. These try to show how the magnetic field and the flowing plasma affect each other in complex ways. The study of this star's behavior in contrast to that of other magnetic O-type stars helps astronomers learn more about how magnetic fields change in massive stars and how they affect the later stages of stellar evolution. Investigating these magnetic O-type stars is more than just a theoretical exercise. It has far-reaching consequences for several areas of astrophysics. For instance, how these stars lose mass and rotational momentum can show whether they will finally explode as supernova or fall apart straight into black holes. Their magnetic features also change how the chemicals inside the star mix, which could change the rates of nucleosynthesis and the enrichment of the space between the stars. In addition, these stars are used to test ideas about the attraction of stars in conditions that are much harsher than those found in stars with less mass, like the Sun. Binary systems and stellar interactions. Binary systems and stellar interactions are a new and exciting area of astrophysics. The gravitational dance between two or more stars creates strange effects that make us think about how stars evolve. When these systems are close together, mass transfer, tidal forces, and sometimes even dramatic mergers can happen. All of these things can change the life cycles of the stars involved in big ways. Astronomers can study the physical processes behind eclipses, changes in orbital times, and changes in spectral fingerprints by looking at large sets of data that show when and how these things happen. RRA is an interesting case study of how binaries interact with each other because its irregular eclipses and changing orbital parameters show that it has had a lot of complicated interactions in the past. Over many years, this system with regular eclipses has been carefully watched, and its light curves have shown clear changes in when and how long eclipses last. These oddities point to the fact that the two parts are exchanging mass and rotational momentum all the time, which has a direct effect on how their orbits move. The orbital period of RRA is not constant. Instead, it exhibits gradual changes over time, hinting at ongoing mass transfer between the two stars. In such systems, when one star expands, often due to evolutionary processes, and begins to overflow its Roche lobe, material can stream toward its companion. This mass transfer not only alters the masses of the individual stars, but also affects the system's overall orbital configuration. As the donor star loses mass, its gravitational influence wanes, which can result in a widening of the orbit. Conversely, if the accreting star gains significant mass, the orbital separation might contract. The subtle shifts observed in RRA's eclipse timings are direct evidence of these competing processes at work. Along with mass movement, wave interactions are very important in determining how RRA moves. As the stars move around close to each other, their gravitational pulls cause changes in the tides that can cause rotational momentum to be exchanged. The stars' rotating periods and orbital periods tend to be in sync with these tidal forces, but in RRA, they are not perfectly in sync. These problems with timing can cause the orbital period to change even more, which can make the patterns seen in the light curves during eclipses even more difficult to understand. Mass transfer, tidal forces, and maybe even magnetic interactions all work together to make a complicated system that is always changing. This makes the rigid models that are usually used to describe eclipsing pairs look wrong. Spectroscopic studies of RRA have revealed that the star's spectral lines exhibit shifts and asymmetries that vary with the orbital phase. These variations provide critical insights into the velocity fields within the binary, indicating not only the presence of a stream of material flowing from one star to the other, but also turbulence and localized disturbances that can further affect the orbital dynamics. By analyzing these spectral features, astronomers have been able to construct detailed models of the mass transfer process, revealing that the rate of mass exchange may itself vary over time. This variability in mass transfer rate further contributes to the changing orbital parameters, making RRA a dynamic and evolving laboratory for studying binary evolution. RRA shows how important long-term observations are for knowing how paired stars change over time. Its orbital period and eclipse traits change slowly over time, and these changes can be hard to notice. They show how star interactions change a system over time. These kinds of findings not only make our theoretical models more difficult, but they also force scientists to improve simulations that show how mass loss, angular momentum transfer, and tidal synchronization are all connected in complex ways. Systems like RRA will continue to be important standards that theories of binary evolution are tried and made better against as computer models get smarter. Eclipsing binaries, dynamics of mass transfer, and orbital evolution. Contact binaries are another interesting group of systems where the binary parts are in contact or very close to being in contact. The stars in these systems share a shell, and mass exchange happens all the time. The orbits change because of complicated interactions between the stars' turbulent bands and their gravitational fields. Observationally, these systems can show big changes in period, which can sometimes even show the start of a merger event. In contact binaries, the delicate balance between mass transfer, rotational momentum loss, and tidal forces makes it a great place to test theory models, since even small changes can cause big changes in the orbital configuration. Some eclipsing binaries exhibit peculiarities that suggest the presence of additional companions or complex multi-body interactions. In such systems, the gravitational influence of a third star can induce periodic variations in the orbital elements of the binary pair, a phenomenon known as the light travel time effect. These tertiary interactions can cause the observed eclipse timings to oscillate, complicating the interpretation of the system's intrinsic mass transfer dynamics. The study of such triple systems not only enriches our understanding of binary evolution, but also offers insights into the formation and stability of hierarchical multiple star systems in general. The physics of mass movement in these systems have big effects on how we think about how stars evolve. When a star loses mass to its partner, it can change the way it evolved in a big way. For example, a donor star that loses a lot of mass might grow more slowly or have a completely different outcome than a star that stays alone and has the same starting mass. On the other hand, the star that is accreting may become rejuvenated and look younger or hotter than expected. These processes are necessary to explain the observed variation in stellar populations. They are also necessary to explain the creation of blue stragglers, stars that look incredibly young compared to their surroundings, and other strange objects like subdwarf B stars. The study of eclipsing binaries with unusual interactions has important ramifications for distance measurements in astronomy. Many of these systems serve as standard candles due to the predictable nature of their eclipses and orbital dynamics. However, when mass transfer or third-body effects complicate the picture, astronomers must carefully calibrate their models to account for these perturbations. Gamma Velorum and the complex dynamics of multi-star systems. Gamma Velorum is an interesting and well-studied example of a complex multi-star system. It is best known for having a Wolf-Rayet star as one of its main parts. This system shows how stellar evolution and gravitational dynamics combine, giving us important information for learning about the life cycles of huge stars and the complicated interactions that happen when there are many stars together. Gamma Velorum is made up of a Wolf-Rayet star, a very old huge star that has shed many of its outer layers, and an O-type star that is close by. The Wolf-Rayet component is known for its strong star winds, huge mass loss, and bright emission lines in its spectrum. The star's top layers have been stripped away, revealing the products of nuclear fusion happening in its core. This means that the star is in a late evolutionary phase. Having a Wolf-Rayet star in a pair or multiple system like Gamma Velorum not only makes our ideas about how stars change over time more difficult, but it also gives us a unique chance to study how strong winds and radiation affect nearby stars. These observations show a rich patchwork of emission and absorption patterns that change over time. The strong wind from the Wolf-Rayet star reacts with its massive O-type companion strong radiation field, causing areas of gas that are shocked and stirred up. This exchange changes not only how the energy is spread out in the system, but also how fast mass is lost overall, and how the stars change over time. The combined spectrum of Gamma Velorum is made up of input from both stars. It is very hard to separate these spectral marks. To split the overlapping spectral lines and figure out how the high-energy processes happen in the win-win collision region, we need to use advanced modeling methods. These kinds of studies put important limits on theoretical models of stellar winds and binary interactions. This helps scientists learn more about how big stars lose mass and change over time. There are a lot of problems and effects that go beyond the details of any one object when you study multi-star systems like Gamma Velorum. The stars' gravitational pull on each other can change their paths a lot over time, which is a big problem. When stars are close to each other, tidal forces can change their shapes, make their rotating times match, and even cause oscillations or pulsations that change the light curves that we see. The way these gravity effects change the system over time can hide or look like other astronomical events, which makes it harder to figure out what the observations mean. If the spectral lines move on a regular basis, it could be because the star itself is changing or because it is moving around a shared center of mass. So scientists have to use complex models and long-term observations to figure out which factors are affecting the event. It can be hard to separate the visible features of stars that are part of systems with more than one star. Since light from more than one star is mixed together, the spectrum we see is a mix of traits from each star. Because stars are made up of many different parts, it is hard to get exact measurements of their temperature, chemical makeup, and radial motion. When looking at Gamma Velorum, the job is to separate the Wolf-Rayet star's emission lines from the O-type companion's absorption lines. To do this, high-resolution spectroscopy and spectral disentangling methods are used along with other advanced spectroscopic techniques. These methods not only give us a better idea of what each star is made of, but they also show us how they interact with each other in complex ways, like when winds collide and shock fronts form, which can change the spectra over time. Multi-star systems provide valuable insights into the broader processes of stellar evolution and galactic dynamics. Binary and multiple star systems are common throughout the galaxy, and their interactions can lead to a range of outcomes that influence the chemical enrichment and dynamical evolution of their host galaxies. For example, mass transfer in close binaries can rejuvenate stars, leading to the formation of blue stragglers, stars that appear younger than their neighbors. Similarly, interactions in massive systems like Gamma Velorum may be precursors to dramatic events such as supernova explosions or the formation of compact objects like neutron stars and black holes. Understanding these interactions is crucial for developing comprehensive models of how stars live and die, and how their explosive endpoints contribute to the distribution of elements throughout the cosmos. Multi-star systems are also very complicated when it comes to how they form. Gravitational interactions can cause multiple star systems to form in places where stars are forming quickly, like clusters and associations. Stars in these places dance in a very complicated way because of things like dynamical friction, close meetings, and even mergers. So looking at systems like Gamma Velorum gives us a look into the early stages of star formation and how these close-knit groups change over time. Young and forming stars. HL Tauri is one of the most famous and well-studied examples of a young star that is still growing. It is also one of the most important examples for understanding the early stages of stellar growth. Astronomers are amazed by the beautiful protoplanetary disk of this star in the Taurus molecular cloud. This disk is made up of moving dust that gives a clear view into the processes that shape the formation of stars and planets. A lot of detailed studies, mostly with the Atacama Large Millimeter Submillimeter Array, ALMA, have shown a lot of interesting features about HL Tauri's disk. These include rings and gaps that are very close together, which could mean that planets are forming there, or that other dynamic processes are at work. These studies not only help us understand the disk's chemical and physical makeup, but they also test current ideas about how quickly and easily stars and planets can form. The protoplanetary disk around HL Tauri is rich in both gas and dust, offering a snapshot of a star in its nascent phase. The disk's structure, with its alternating bright and dark regions, indicates that material is not evenly distributed. One prevailing interpretation is that the gaps in the disk may be carved out by the gravitational influence of nascent planets. Alternatively, these features might also result from variations in the disk's temperature or chemical composition, which could lead to differences in dust grain growth and settling. The sheer complexity of HL Tauri's disk suggests that planet formation processes might begin much earlier in a star's life than previously thought. Its disk is relatively massive and exhibits signs of rapid evolution, implying that the material within these disks can coalesce into planetesimals and eventually into fully formed planets on timescales of a few million years or even less. These revelations have significant implications for our understanding of how common planetary systems may be and how quickly they can emerge following a star's birth. Its disk structure, H.L. Tauri's overall environment, provides a wealth of information about the physical conditions in star-forming regions. The star itself is deeply embedded in a dense molecular cloud, where gravity is causing the collapse of gas and dust that eventually gives birth to a new star. This ongoing accretion process is not only observable in the disk, but also in the energetic emissions from the star, which can include outflows and jets that help regulate angular momentum. Such feedback processes are critical for understanding the balance between the forces that drive collapse and those that counteract it, determining the final mass and evolution of the star. By examining H.L. Tauri, researchers can refine models of early stellar evolution, particularly the phases where accretion and disk dynamics play pivotal roles. Beyond H.L. Tauri, the larger group of T Tauri stars shows a different important stage in the birth of a star. T Tauri stars are new, low-mass stars that are still getting smaller as they move toward the main sequence. These galaxies are known for their strong changes, bright emission lines, and often the presence of rings around the stars. Most of the time, these stars are younger than 10 million years old and show how stars change before they reach the main sequence. T Tauri stars are notable for several distinct characteristics that make them invaluable for studying stellar formation. One of their defining features is their pronounced variability, which is believed to arise from both intrinsic factors, such as pulsations and magnetic activity, and extrinsic factors like variable accretion rates from the circumstellar disk. Their light curves often display irregular fluctuations, which have been attributed to hot spots on the stellar surface where accretion is most intense, or to the rotational modulation of large star spots. This variability offers clues about the internal processes of the star, such as convection and the operation of a magnetic dynamo, which are critical in regulating the transfer of angular momentum. The wide range of emission lines that T Tauri stars have is another important thing about them. These spectrum traits, especially the strong H-alpha emission, show that active accretion is happening and that material is present around the star. These bright emission lines are caused by accretion shocks, which happen when material from the disk falls onto the surface of the star. They heat the gas around the star. Through careful spectroscopic studies of T Tauri stars, scientists can find out how fast stars gain mass during their initial years and measure accretion rates. Another thing that the chemical makeup of the disk and the star itself can tell us is very important information about how things were in the area where stars are formed and how planetary systems are formed. Magnetic fields also play a significant role in the evolution of T Tauri stars. These young stars often exhibit strong magnetic activity, which can regulate accretion by funneling material along magnetic field lines onto the stellar surface. This process not only influences the star's brightness, but also affects its rotational dynamics and angular momentum evolution. The interplay between magnetic fields and accretion flows is a subject of intense study, as it provides insights into how young stars evolve from chaotic, rapidly accreting objects into stable, main-sequence stars. Observations using spectropolarimetry have revealed complex magnetic topologies in T Tauri stars, further underscoring the importance of magnetism in the early stages of stellar evolution. The significance of T Tauri stars extends beyond the stars themselves. Their circumstellar disks are the birthplaces of planets. By studying the structure and evolution of these disks, astronomers can glean information about the processes that lead to planet formation. Variations in disk density, temperature gradients, and dust grain growth are all factors that influence the eventual formation of planetesimals and protoplanets. V1057 Cygni is a striking example of the Fu Orionis phenomenon. This is a group of young stars that erupt suddenly and dramatically, making them several times brighter for a short time. Before it erupted, V1057 Cygni was a pretty normal protostar that slowly gathered matter from its ring around the star. A quick and intense burst of accretion, on the other hand, changed its look dramatically, turning it into a beacon that scientists all over the world were drawn to. During this explosion, the brightness goes up quickly and then slowly goes down over a period of years or decades. It is thought that the quick release of energy was caused by problems in the accretion disk around the star. There, heat and gravitational forces may have suddenly become too strong for the disk to hold its own pressure. When this kind of rapid accretion happens, a huge amount of matter crashes onto the star's surface, releasing gravitational energy in the process. This causes the star to temporarily become much brighter. As shown by V482 Cygni, the Fu-Orionis phenomenon questions our usual ideas about how stars form by showing that explosive events can happen in between the birth of a star. These events aren't just interesting for a short time. They change the star's structure and evolutionary path in basic ways. There are noticeable changes in the star's spectrum, including a move toward cooler temperatures and the appearance of wider absorption lines. These changes show that the star's outer layers are growing quickly. Over time, as the rate of accretion slows down and the material that is thrown out spreads out, the star slowly returns to a more stable state. Such an explosion can, however, have long-lasting effects that change how both the star and the disk around it evolve over time. The big changes seen in V482 Cygni are a great way to learn about the physics of disk instabilities and mass accretion processes. They also help us understand how young stars grow and change in the wild places where stars are being formed. Besides Fu-Orionis events, bright red novae are another interesting type of transient event in the universe. Many scientists now think that these events are proof of stellar mergers, which are terrible events in which two stars circle inward and join together to form a single, heavier object. In contrast to supernovae, which are very powerful blasts, luminous red novae are a more gentle but still impressive release of energy. There is a steady rise in brightness that peaks and then fades over the course of months to years in the light curve of a brilliant red nova. There is also a clear red hue. This red color is a sign of the envelope of cooling and expanding matter that is thrown out during the merger. For bright red novae, the merging process is at the heart of the short-lived event. When two stars are close to each other, they can interact and lose rotational momentum, which makes them spiral together over time. As the stars combine, the gravitational potential energy they release is turned into kinetic and thermal energy. This causes an explosion that makes the system brighter for a short time. The material that is released, which is made better by mixing the insides of stars, cools and condenses into dust, which helps the nova look red. Studies of these events, such as spectroscopic studies and thorough light curves, show that stellar mergers are a big part of how close binary systems change over time. These ideas also help explain how some of the biggest stars formed in ways that don't fit nicely into usual ways of explaining evolution. The occurrence of luminous red novae offers several important implications for astrophysics. First, these events serve as a natural laboratory for studying the physics of stellar collisions and mergers. The complexities of mass exchange, energy dissipation, and angular momentum redistribution during such a merger challenge existing models and prompt the development of more sophisticated simulations. Second, luminous red novae contribute to the chemical enrichment of the interstellar medium. The merger process can dredge up material from deep within the stars, releasing newly synthesized elements into the surrounding space. Over time, this enriched material becomes part of future generations of stars and planets, influencing the overall chemical evolution of galaxies. Additionally, studying these short-lived events shows the variety of ways that stars can change over time. Over the years, supernovae have been thought of as the explosive ends of massive stars. However, bright red novae show another possibility. Two lower-mass stars merging could create a new object with a different evolutionary path. In places with a lot of stars, like star clusters, This process is especially important because it can bring close pairs together through gravity forces. High velocity and runaway stars. Out of all the stars in our galaxy, some manage to break free from the Milky Way's pull and speed through space at speeds that almost seem out of this world. One of these objects, which was first named SDSS J090745, 0 plus 024507, has come to represent this very small group of runaway stars. Astronomers are very interested in this star because it is moving so fast that it looks like it will leave the Milky Way and go somewhere else. It is commonly called the hypervelocity star. The study of this star gives us a unique chance to look into the physical processes that can speed up stars to such great speeds and the changing relationships in our galaxy that cause these things to happen. The origin of the hypervelocity star is rooted in the violent gravitational interactions that occur in dense stellar environments. One of the primary theories posits that such stars can be ejected by interactions with the supermassive black hole residing at the center of our galaxy. In this scenario, a binary star system wanders too close to the black hole, and the intense gravitational forces disrupt the system. As the binary is torn apart, one star may be captured into a tight orbit around the black hole, while the other is flung outward at tremendous speeds, often exceeding 1,000 kilometers per second. This Hills mechanism, named after astronomer Jack Hills, who first proposed the idea, offers a compelling explanation for the extreme velocities observed in these objects. The hypervelocity star's measured speed is consistent with predictions from this model, suggesting that a close encounter with the Milky Way's central black hole could be responsible for its rapid journey across intergalactic space. Dynamical reactions in dense star groups are another possible way this could happen. In places where a lot of stars are born, close gravity encounters between stars can cause complicated three-body interactions. When these kinds of collisions happen, one star can gain a lot of kinetic energy at the cost of its partners. This can cause a runaway star to be thrown out at a very high speed. Many people think that interacting with a supermassive black hole is the best way to make hypervelocity stars, but dynamical ejections in clusters are also possible, especially when there is a huge binary or multiple star system involved. Seeing fast stars like these in other galaxies supports the idea that hypervelocity ejections can be caused by more than one thing, and each thing has its own astronomical fingerprints. For example, its chemical makeup can be used to find out where it came from. If the star was thrown out from near the center of the galaxy, we might see chemical enrichment patterns that are typical of that area. For example, higher amounts of metallicity could be caused by generations of stars forming close to the black hole. If, on the other hand, the star came from a crowded clump in the galactic disk, its chemical abundances might be different. In-depth studies have shown that its chemical makeup is consistent with forming in a place where there are strong interactions between stars and a long past of stars forming. The hypervelocity star didn't just appear out of nowhere. These results add to the idea that it was part of a changing system where gravity forces sped it up to such high speeds. The study of fast-moving stars like this one has big effects on how we think about the structure and history of the Milky Way. The paths they are taking give us a unique chance to look into the gravitational pull of our galaxy. Astronomers can figure out how the Milky Way's gravitational field is shaped by following the tracks of these stars. This helps them figure out where the mass is distributed, including both luminous matter and the mysterious dark matter. Hypervelocity stars are natural test particles that help improve models of how galaxies move and how mass is spread in our galaxy and how it interacts with the groups of stars that are already there. The extreme velocities of hypervelocity stars challenge our understanding of stellar evolution under unusual conditions. As these stars travel through intergalactic space, they are subjected to environments that differ markedly from the dense, radiation-rich regions where most stars reside. The impact of such isolation on a star's evolution is an open question, inviting further theoretical and observational research. Some researchers speculate that as hypervelocity stars age, they might exhibit atypical evolutionary pathways, potentially revealing new insights into the late stages of stellar life, such as unusual white dwarf cooling processes or peculiar supernova progenitors. Runaway and rapid motion stars. A famous example of a runaway star is Zeta Puppis. A runaway star is an object that has been thrown out of its home and is moving through space at speeds fast enough to avoid the gravity of its parent cluster or even the galaxy. As an O-type supergiant, Zeta Puppis has the amazing properties of being very bright and losing a lot of mass. This makes it a great object to study what happens after dynamic interactions happen in dense star settings. Not only does its path through the Milky Way show how dramatic things can get when stars are changing, but it also gives us important information about how stars are ejected. The origin of Zeta Puppis as a runaway star is most likely tied to powerful gravitational interactions that took place in a dense cluster environment. One leading theory involves the dynamical ejection mechanism, where close encounters among massive stars in crowded clusters can result in one or more stars being accelerated to high velocities. In such environments, gravitational interactions are intense, and even a slight perturbation can send a star careening out of the cluster. Alternatively, the binary supernova scenario may also play a role in explaining Zeta Puppis's rapid motion. In this model, a star in a binary system is propelled to high speeds when its companion undergoes a supernova explosion, effectively disrupting the gravitational bond between the two stars. The remnant, now unbound from the system, carries away a significant amount of momentum. Observational data on Zeta Puppis, such as its measured velocity and trajectory, support the idea that it is indeed a runaway, likely having been ejected from a region of intense stellar formation and dynamic interactions. Zeta Puppis research has effects that go far beyond just figuring out how one star moves. Astronomers can figure out a lot about the conditions where it was born, and the physical processes that caused it to be ejected by looking at its speed, direction, and chemical makeup. For instance, the star's fast speed limits the gravitational pull of its birthplace, which gives us information about how mass is distributed in young, dense groups. By looking at Zeta Puppis's chemical makeup, we can also find out if it has gone through any strange evolutionary processes or interacted with other stars, which will help us learn more about how huge stars evolve. Its position as a runaway star also has larger effects on the structure of the galaxy. Following its path through the Milky Way helps us learn more about the gravitational field and the spread of dark matter, which affect the paths of fast-moving objects. Bold stellar winds and a lot of mass loss are features of Zeta Puppis, which are typical of huge O-type supergiants. These traits are part of the star's development, but they are made worse by the fact that it is runaway. Zeta Puppis moves quickly through the space between stars. Its strong winds combine with the material around it, making bow shocks and complex patterns of charged gas. These interactions not only change the star's near surroundings, but they also give us proof that we can use it to test models of how stellar winds work and how moving quickly affects mass loss. While Zeta Puppis exemplifies the dramatic ejection of a massive star from a dense stellar region, other rapid motion stars in our neighborhood also offer valuable insights into past gravitational interactions and the dynamical history of the Milky Way. Stars such as Gliese 445, Barnard star, and Wolf 359, although less massive than Zeta Puppis, exhibit high velocities that are equally intriguing and significant for understanding galactic dynamics. Gliese 445 is a close red dwarf star that stands out because of how fast it moves compared to the Sun. It is thought that this star's fast speed is caused by changes in gravity, possibly from close encounters with large objects or even the remains of supernova events in the past. Astronomers can figure out its path by measuring its proper motion and radial velocity. This often gives them hints about an exciting past with dynamic interactions. The study of Gliese 445 not only helps us understand how red stars move, but it also helps us figure out the gravity field around our galaxy. According to its movement, nearby large structures and dark matter's gravitational pull are very important in speeding up stars. This is a key test for models of how the galaxy moves. Barnard's star is another great example of a fast-moving star. It is a red dwarf that has one of the fastest proper movements in the sky. Even though it doesn't have a very bright light, its very fast speed suggests that it has had strong gravity impacts in the past. Barnard's star is moving quickly through space, as seen by observations. Its path may have been changed by close encounters with other stars or by being thrown out of its original stellar group. Astronomers can learn about how the Milky Way has changed over time by studying stars with such high proper motion. The star's speed and direction can help us figure out where it came from by showing us how star groups used to be organized and how gravity interactions affected them. Barnard's star is also an important reference point for learning about how lower-mass stars, which don't look as interesting compared to O-type stars with a lot of mass, affect the galaxy's general dynamical history. It is interesting to study Wolf-359, another red dwarf star in our solar neighborhood, because it has a fast average speed through space. Even though it's not very bright in our sky, the fact that it moves quickly says that it has also been shaped by gravity waves in the past. Like Barnard's star and Gliese 445, Wolf-359's movement can be used to figure out what gravity pulls it felt as it traveled through the Milky Way. The fast speeds seen in these stars are strong proof that the kinematic landscape of our galaxy is still being changed by dynamic processes like interactions between star groups, gravity slingshot events, and perturbations by massive objects. These fast-moving stars, Zeta Puppis, Gliese 445, Barnard's star, and Wolf-359, give us a lot of different ways to look at how stars move. As Zeta Puppis shows, violent ejection processes in huge stars can have dramatic effects. However, the red dwarf's high speeds show that even stars with less mass can experience strong gravitational acceleration. Their paths are like cosmic skeletons. They record past encounters and help us understand how mass, including dark matter, is distributed in the Milky Way. Astronomers can figure out the past of gravitational collisions in our nearby galaxy by looking at the kinematics and chemical makeup of these stars. This not only helps us learn more about how stars move, but it also gives us a bigger picture of how galaxies change over time. Additional strange stars, exploring the outliers in stellar diversity. Dualities like WR104 are very rare and show how the strong winds from two stars can combine in interesting ways. A Wolf-Rayet star in this system loses its top layer of hydrogen, revealing layers inside that are full of helium and stronger elements. When the strong winds from this stripped star meet those from its nearby O-type partner, they make a rough and complicated crash zone. The interactions not only make the dust around the system look nice in a circular shape, but they also teach science things about other stars that are hard to find. When the winds from two different stars crash into each other, they make shock waves that let dust grains form even in hard environments with a lot of radiation. The spiral dust plume that forms is not random. It forms in loops that may help us figure out where the stars are going and how fast they are losing mass. Now, scientists think that small changes in the stars' orbits, like how they circle each other, can have an impact on where and how the dust forms. These features call into question older ideas about how dust forms and show that small changes can have big effects even in very strong, high-energy places. The exposed layers of the Wolf-Rayet star give us a rare look at the later stages of nuclear burning. Because most of the hydrogen is gone, the star's light now comes from deeper layers where helium and heavier elements are being produced. This situation is like looking at a secret inner room that reveals how the star has processed its fuel over time. It helps scientists understand the stages just before a massive star dies and how it might enrich the space around it with new elements. The circular pattern of dust around WR104 is also very interesting because it shows how the star behaved in the past. The spiral's loops could each show how much mass was lost at a certain point in the circle. Researchers can guess things like the rate of mass loss and the speed of the winds by looking at these loops. Located near the Milky Way's center, the Pistol star is one of the most luminous and massive stars known. Its name derives from the shape of the nebulous structure surrounding it, which resembles a pistol. The Pistol star is a luminous blue variable, and its extreme properties challenge our understanding of the upper mass limits of stars. With an estimated mass of over 100 solar masses and a luminosity that can exceed several million times that of the Sun, this star radiates an enormous amount of energy. The Pistol star's fast rate of mass loss is one of the most interesting things about it. The star shoots out matter at very high speeds because of strong radiation pressure. This helps to make the Pistol Nebula, which is a huge, complicated ring of charged gas and dust. In addition to showing what the star's violent past looked like, this nebula also helps us understand how very big stars lose mass. The Pistol star's behavior is very important for forming our models of bright blue variables, and for how big stars control their growth and evolution in the harsh conditions close to the centers of galaxies. Gamma Cassiopeiae is an interesting variable star that changes brightness quickly and in strange ways. It is a B star, and its spectrum shows strong emission lines, which mean it has a ring around it made of material thrown out by the star. Gamma Cassiopeiae's light changes over time. This is thought to be due to a mix of fast-spinning and pulsational instabilities, which push material off of its surface on occasion. This star is of particular interest because its behavior challenges our understanding of how mass is lost in rapidly rotating stars. The circumstellar disk around Gamma Cassiopeiae is not static. It is subject to fluctuations in density and structure, which lead to changes in the star's brightness and spectral features. The irregular and often unpredictable variability observed in Gamma Cassiopeiae provides important constraints on the mechanisms of angular momentum loss and disk formation in massive stars. Melnik 42 is one of the biggest and most active stars in the Tarantula Nebula, which is known for having a lot of star formation going on. That this star is especially interesting is because of how bright it is and how harsh the conditions are around it. As part of a dense star cluster, Melnik 42 is affected by strong gravitational pulls and stellar winds from nearby huge stars. These can change how it evolves and cause dynamic interactions. Melnik 42 is very bright, which means that it is undergoing strong nuclear fusion in its core. This fusion produces strong star winds. These winds cause the star to lose a lot of mass, and they are also very important in forming the shape of the nebula that surrounds it. The study of Melnik 42 gives us important information about how the biggest stars affect the places they are in, which in turn affects the birth of new stars and the chemical history of the area. Specifically, the interactions between Melnik 42 and the stars nearby can create complicated structures in the space between the stars, like shock fronts and ionization regions. These structures are very important for understanding how stars in dense clusters age. Also, Melnik 42's harsh conditions make it a great place to study the limits of how stable stars can be. High radiation pressure and rapid mass loss make it hard to use current theories. This forces astrophysicists to rethink how gravity and radiation work in the heaviest stars. HD 93129A is one of the brightest and hottest O-type stars, residing in one of the most active star-forming regions in our galaxy. As an archetype of extreme O-type stars, it is characterized by its blistering temperatures, intense luminosity, and powerful stellar winds. These properties make HD 93129A an important object for studying the upper limits of stellar mass and the mechanisms of energy transport in massive stars. The star's tremendous energy output is driven by vigorous nuclear fusion in its core, and its strong stellar winds are capable of ejecting vast amounts of material into the surrounding space. These winds interact with the local interstellar medium, contributing to the formation of bow shocks and influencing the dynamics of nearby gas clouds. HD 93129A's exceptional brightness and mass loss rates challenge traditional models of stellar evolution, which must account for the rapid changes in mass and energy output observed in such extreme environments. V532, also called Romanos star, is a strange variable star in the Andromeda galaxy. This object's light changes dramatically, which makes it different from most LBVs. These changes go against what we normally think about how stars change over time. Romanos star goes through periods of strong explosions, during which its brightness can change a lot in a short amount of time. These are followed by periods of quiescence, during which the brightness slowly returns to a normal level. The erratic behavior of Romanos star is believed to be linked to the instability in its outer layers, where rapid mass loss and changes in temperature lead to observable variability. Its spectrum reveals signatures of both high and low ionization states, suggesting that the star undergoes significant changes in its atmospheric conditions during its outburst phases. The study of V532 provides valuable insights into the physical mechanisms driving variability in luminous stars, as well as the potential impact of binary interactions, which may further complicate its behavior. HD 108 is another big star that is hard to put into a single category. Astronomers have been confused for decades by this O-type star's wide range of spectral variations and strange wind qualities. Big changes happen over time in the star's spectral lines, which shows that its outer layers are moving around. It is thought that these changes are caused by changes in its star wind, which may have something to do with magnetic activity or unstable pulsations. The key to understanding HD 108 is to look at how its great brightness and changing spectral traits interact with each other. Strong stellar winds are caused by the star's strong energy, but these winds seem to be affected by other processes that we don't fully understand yet. Different ideas say that the spectrum changes we see might be caused by localized magnetic fields that shape the wind into organized streams. On the other hand, pulsations in the star's upper layers could sometimes make the wind stronger or weaker, creating a spectrum that is dynamic and always changing. People are interested in MWC 349A because it is a truly unique star that gives off very strong maser waves. Masers are like lasers in the universe, but they boost microwaves by stimulating the release of radiation. MWC 349A is one of the strongest star maser sources known. Strange features in the star's spectrum and strong radio signals show that it is ringed by a thick ionized disk that is perfect for master action to happen. The presence of such intense maser emissions makes MWC 349A an invaluable laboratory for studying the physical conditions in circumstellar disks. These emissions allow astronomers to probe the kinematics, density, and temperature of the gas very close to the star. Observations have shown that the disk around MWC 349A is rotating at high speeds, and the maser spots provide detailed information about the disk structure. The study of MWC 349A not only advances our understanding of maser physics but also offers insights into how massive stars interact with their immediate environments. The dynamics of the disk, combined with the star's own energetic output, contribute to a complex picture of mass loss and angular momentum redistribution in the early stages of stellar evolution. Beta Lupi is yet another strange star that is hard to put into a single category. Even though it's not as big or bright as some of the other things we've talked about, this object changes in strange ways that make us question what we think we know about how stable stars are. The star's light changes in strange ways that can't be easily explained by pulsation models or pair interactions. These differences show that Beta Lupi may be going through complicated internal processes, which could be linked to changes in its flow patterns or magnetic activity in certain areas. Studies of Beta Lupi's light curve and spectral properties have shown that its changes may be connected to short-term mass loss events or small changes in the structure of the star itself. This kind of behavior is very unusual for stars of this type, and it makes us wonder about the physical processes that cause these changes. Astronomers hope to find out what causes Beta Lupi's strange changes in brightness by keeping a close eye on it for long periods of time. In turn, this can tell us a lot about how stellar convection, magnetic fields, and pulsational dynamics work together in stars with less mass. Beta Lupi's unusual variability has broader implications for our understanding of stellar evolution. The fact that a relatively ordinary star can exhibit such complex behavior suggests that there may be a continuum of variability mechanisms operating across different classes of stars. This realization challenges the dichotomy between stable and unstable stars, indicating that even stars that appear relatively normal may harbor hidden instabilities that influence their evolution over time. Our journey through the universe's strangest stars has unveiled a fascinating realm of cosmic mysteries that challenge what we know about the cosmos. If a particular star caught your imagination, let us know in the comments. Don't forget to like, share, and subscribe to keep exploring the wonders of the universe with us.